A'udhu billahi minash shaitani rajim. Bismillahir rahmanir rahim. Short key noise can be a significant issue in wireless electronic circuits, particularly in high frequency communication system. And in wireless application, the presence of short key noise can affect the overall performance and signal quality of the system. In wireless communication system, Schottky diodes are often used as mixers, detectors, or frequency multiplier due to their fast switching speed and sometimes very low capacitance. However, these diodes also contribute to the other types of noise in the system, including Schottky noise. When Schottky diodes are used in wireless circuits, noise generated by these diodes can mix with the desired signal and create some interferences, which leading to degrade the received signal quality. And these interferences can overall affect the receiver's ability to detect and process weak signal, and reducing the overall sensitivity and dynamic range of the system. In this unit, we will discuss dif- different basic concept of the Schottky diode and different name of the Schottky diode, Schottky noise. Then we discuss about the Schottky current, Schottky spectral density, and finally we discuss about the application of Schottky noise in wireless amplifiers. Short noise, also known as Schottky noise, quantum noise, or Poisson noise. This type of noise can be modeled by Poisson random process. Shortcut type of noise that arises from a discrete nature of electric charge and statistical fluctuation in the arrival of the charge carrier. Short noise also occurs in photon counting in optical device, where short noise is associated with the particle nature of the light. Short noise, a Schottky noise is present in various electronic devices and systems, particularly those involving the flow of electron and hole as electric current. The fundamental cause of Schottky noise is the random nature of electron or other charge carrier emission, detection, and transportation inside the device. When a current flow through a conductor or semiconductor device, such as diode transistor, individual charge carriers have statistical arrival pattern due to the random scattering with the molecular structure of the devices or metal or other devices, semiconductor devices. Short noise is characterized by a random fluctuation in current or voltage due to discrete nature of the charge carrier. It follows a Poisson distribution and proportional to the square root of the average current or the square root of the average number of charge carriers passing through the point in a given time. The Schottky noise spectral density S can be described by the short noise equation S is equal to 2qi delta L. Schottky noise current is a significant source of noise in Schottky diode and other devices utilizing Schottky junction. It can limit the sensitivity as well as the performance of high frequency detectors, mixers, and many other applications where Schottky diode are employed. Techniques to minimize the Schottky noise include using material with low barrier height between metal and semiconductor, optimizing the diode structure and geometry, and employing some noise reduction measurement such as shielding and proper filtering. Mean square Schottky noise current for a diode can be written as I square is equal to 2I plus I naught multiplied by QB, where IN is root mean square current density, I naught is reverse saturation current, and Q is the charge of the electron, 1.6 into 10 power minus 19 coulombs. And I is the direct current in ampere. B is the bandwidth in hertz, and the ideality factor sometimes used is a parameter that accounts for the deviation from ideal Schottky junction. It takes into consideration factors such as quality of the metal, semiconductor interferences, recombination, electron hole recombination process, and other non-ideal behavior of the type. The ideality factor is typically greater than 1 and this affects the magnitude of the Schottky noise current. And similarly, the reverse saturation current in most of the cases is very small, so it is neglected in many cases when we apply Schottky current equation for the design of the wireless-based electronic systems. Schottky noise spectral density, denoted by S, is a measure of the power spectral density of Schottky noise. It represents the distribution of the noise power over different frequencies. The Schottky noise spectral density is commonly used to analyze and characterize the nature of the noise or the noise behavior of the device that exhibits Schottky noise, such as a Schottky diode, bipolar junction transistor, and many other electronic devices. The expression of Schottky noise spectral density is actually derived from the Schottky noise current equation, and it is given as S is equal to 2q I delta S, where S is the Schottky noise spectral density in watts per hertz, Q is the charge of the electron, and I is the average current in amperes, and delta F is the bandwidth of the measurement of analysis in hertz frequency. Amplifier is an integral part of any transmitter, repeater, electronic receiver. Actually, the device is requires some communication. In an amplifying device such as transistor, the Schottky noise is inversely proportional to the transconductance of the device, which is represented by Gm. This relationship can be understood by considering the contribution of various noise sources in the device. In transistor, the transconductance is a measure of the device's ability to convert input voltage variation into output current variation. It is a key parameter that determines the gain and linearity of the amplifier. The transconductance is directly related to the device small signal current gain. The Schottky noise in a transistor arises due to the random nature of the charge current and across the Schottky diode or some other interferences with the device. This noise is proportional to the square root of the average current flowing through the junction as discussed earlier. When the transconductance of the transistor is increased, it means that device is more efficient to convert input voltage variation into output current variation. In other words, for a given input signal, the higher transconductance result in higher output current swing. When output current is increased, the noise contribution from the Schottky diode or Schottky noise also increase because it is directly proportional to the average current. However, the noise power spectral density, noise power per unit bandwidth can be defined as a power spectral density as in previous slide. It is remain constant. Therefore, when the transconductance increase, the noise power remain constant, but the output current increases. Consequently, the Schottky noise voltage, which is proportional to the square root of the current, decreases. This is why Schottky noise is inversely proportional to the transconductance of amplifying device. It is worth noting that while increasing the transconductance can reduce the Schottky noise. It may be introduce many other type of noise associated with the device, such as a thermal noise or flicker noise or partition noise, any type of noise can also be increased. Therefore, a careful trade-off between the different noise sources and device performance is necessarily in the design of an amplifier for wireless communication system.